In the physical world, motion is continuous. When intense, unrelenting pressure forces a heavy steel beam to buckle, the metal deforms in a smooth, unbroken progression. But computers cannot simulate an infinite number of moments. They are finite processing machines. To bridge this gap, engineers rely on discretization. They chop the continuous flow of reality into distinctly calculable slices, known as time steps. We can see this clearly in a baseline dynamic model. A mass oscillating on a spring naturally plots a perfect continuous sine wave over time. To compute this motion, the system samples the physical movement into frozen, distinct data points. The machine freezes time, calculates the exact state of the physics in that single moment, and then jumps forward to the next frame. Moving the simulation from one frozen data point to the next requires complex mathematical integration. The standard approach relies on implicit methods. This forces the computer to calculate massive, dense, simultaneous equation matrices. The processor must halt at every single time step, taking time to invert these gigantic mathematical grids, strictly to find the next position. In large-scale dynamic analysis, like tracking the propagation of a shockwave, this heavy matrix math drags CPU performance to a crawl. The Leapfrog method is an entirely different architecture, designed specifically to bypass these heavy equation matrices. Bypassing this matrix bottleneck requires a shift in logic. Instead of solving an entire system at once, the math moves toward direct, independent updates for each variable. Most standard algorithms attempt to calculate an object's position and its velocity at the exact same moment in time. The Leapfrog method functions by intentionally desynchronizing these two variables. This chart shows the exact structural layout of that desynchronization. It maps out what is known as a staggered grid. Position, represented by the variable x, is anchored strictly to whole integer time steps, designated as n and n+1. Velocity, represented by v, is offset. It is calculated exactly halfway between those position updates, on the half steps like n+1/2. By staggering the grid, the algorithm ensures that velocity is perfectly positioned to carry the physical object across the gap from one integer step to the next. The pipeline flows through three sequential blocks. First, the computer calculates the current acceleration, an, based on active physical forces. That acceleration pushes the velocity forward by a half step, locking in vn+1/2. This newly minted velocity then pushes the position forward, locking in xn+1. Position leaps over velocity, then velocity leaps over position. The pattern repeats endlessly. Notice what is missing from this cycle. At no point does the loop ask the computer to reference a complex matrix or pause for external processing. The staggered equations create a tightly closed, self-sustaining loop. It continually propels the simulation forward using only its own recent history. In computational mathematics, this specific type of self-contained loop is defined as an explicit formulation. The defining trait of an explicit method is that the future state is calculated entirely and directly from known historical variables. This is a direct contrast to the implicit matrix equations from earlier, which force the computer to guess and balance multiple unknown future states simultaneously. This graphic outlines the resulting engineering benefit. Bypassing that large linear solve drastically lowers the CPU cost required for every single time step. Stripping out that heavy computational weight is exactly why the Leapfrog method is heavily favored for solving complex wave and dynamic problems. The explicit architecture removes the heaviest mathematical roadblocks, turning time integration into a high-speed, lightweight calculation. If each step is so incredibly cheap to compute, the logical shortcut would be to take massive time steps and finish the simulation instantly. But the system is bound by a fatal constraint known as conditional stability. The math only holds together under strictly controlled environmental conditions. Because explicit methods calculate the future directly, without a matrix to check the work, the algorithm blindly assumes velocity remains perfectly constant across the entire time gap. If that gap is too wide, the direct update overshoots the true physical reality, pumping artificial, non-existent energy into the simulation. When the bounds of conditional stability are broken, the error multiplies. The math diverges into complete chaos. The algorithm's greatest strength its blind, uncorrected forward momentum becomes its exact mechanism of failure if the steps are too wide. To prevent mathematical divergence, the time increment, delta t, must remain microscopically small. Simulating just a single second of real time might require millions of tiny individual calculations. This text highlights the core engineering compromise. Explicit methods offer incredibly cheap individual steps, but require a vastly higher total number of iterations. Implicit methods demand expensive individual steps, but they have the stability to safely leap across massive gaps in time without breaking. The Leapfrog method proves that in computational physics, there are no perfect shortcuts. True efficiency requires intelligently restructuring the work to balance raw processing speed against absolute mathematical stability.